All right, we're still looking at ways to build up a redox table from experiments. And when we first did this, we gave you a great big grid where we had like four metals and their corresponding ions, and we told you whether each and every one of those reacted with each and every other one. And that's okay, but I mean, even for four metals, that's 16, theoretically 16 tests that you would have to do. And we'd like to get this done a little more efficiently if we can. And there are ways to do it using a smaller set of reactions like the ones we get here. Each of these is a test where we take two different chemicals, we put them in a bowl, and then we watch and see if anything happens. And maybe something does happen and we get a chemical change, like in this first one, or maybe nothing happens and the chemicals just sit there. So we can use a set like this to build up a redox table. And let's see how it works. We've seen off of our other examples that whenever you have a reaction, there's going to be some kind of, typically a metal ion. It doesn't have to be, but some kind of oxidizer, often a metal ion, that's going to try to oxidize the strongest reducing agent. It's going to try to take electrons from it. And the question is, will it succeed or not? And we know that if your strongest reducer is down here, so this line is like downhill, then that means yes, we get a reaction. And on the other hand, if we have a wimpy oxidizer, let's say calcium ions, and the reducer's way up here, that line is uphill, and that means we get no reaction. So every line in here represents an oxidizer trying to steal electrons from a reducer. And then this line tells us whether it succeeded or not. And on the basis of that, we can figure out who's higher or who's stronger. So here's how these can work. Here we have beryllium metal and cadmium ions. Beryllium can't be an oxidizer. It doesn't have a positive charge. It doesn't want any more electrons, but cadmium does. So I think of this as cadmium ions are trying to steal electrons from beryllium. And how did they do? Well, they succeeded. There was a reaction. Cadmium gained electrons, beryllium lost them. That means if you're building a table, the interpretation of this is that cadmium is higher up on your table than beryllium is. You can think of this as beryllium and cadmium fought over electrons, and cadmium won. Cadmium got the electrons, therefore it must be higher up. It must be a better electron attractor than beryllium is. Next example, hydrogen, positive charge, tried to take electrons from cadmium, and how did that go? It worked again. The hydrogen did gain electrons, cadmium lost electrons. Therefore, on our list, hydrogen must be higher up than cadmium. So over here on my list, I get to try to fit hydrogen in. Sorry, I should be putting the ion charges on this to make it a little clearer. Beryllium is 2. So far our rankings are hydrogen beats cadmium and cadmium beats beryllium. Okay, new reaction. Calcium ions, positive charge, they want electrons. Calcium ions tried to take electrons from beryllium, but nothing happened. It says there was no reaction. So what does that mean? Calcium tried to take from beryllium but couldn't do it. That means beryllium must be higher up than calcium. And finally, hydrogen tried to take electrons from copper, but again, couldn't do it. What does that mean? Copper must be even higher up than hydrogen is. I'll have to fit it in way up here at the top. So high up on the table means you're good at winning fights over electrons. If you're trying to take electrons, you probably will. If you have electrons and someone else tries to take them from you, they will probably fail. And according to this list, copper is higher than hydrogen, which is higher than cadmium, higher than beryllium, higher than calcium. And you can check your table in the data book. And you'll find copper, hydrogen, cadmium, and calcium are all listed on there, and indeed they are in this order. Beryllium is not in my data book, probably not in yours either, but if you found a more complete redox table that had beryllium on it, pretty good chance it would fall between cadmium and calcium if they've set this question up right. Okay, let's see if we can do that again with confidence and speed. Oh, okay, scratch the confidence. We're going to, and maybe also the speed. This one is a little bit different, so we're going to have to look at it more carefully. Over here, I said that the more positive ion or species will generally be trying to take electrons from the more negative one. That's true, but it's a little harder to see with these because now we have negative ions. So in this one, where we have x's with a charge of -1 and y's with a charge of 0, it's actually y, the more positive one, trying to take electrons from x. So in this first reaction, we say y tries to take electrons from x. How did they do? They succeeded. Over here, y has gained electrons. That's why the charge went down. So on our table, y must be higher up than x. Next one, who's trying to take from who here? The more positive species tries to take from the more negative one. So y tried to take electrons from w and couldn't do it. That means w is tougher than y. Y and w fought over electrons and w won. So on the rankings now w is higher. And finally, the more positive one, x, tried to take electrons from z and did. So x is higher up than z. Z must be down here. So that's the order that they'll appear in our list. Now, for both of these, I owe you a little more detail because the question for these says, build a table of reduction half reactions like the one in the data book. So if you just write copper hydrogen, you're not really finishing the question. A full, complete, nice redox table has half reactions in it, where each of these things gains electrons, and then you see it in its reduced state. So oh, here. If you're wondering where that 2 came from, I'll take them out for a minute. I'll do this wrong, and then you'll see why it's wrong, and then we can go back and fix it. Here is one way that you could give the reduction of hydrogen. The trouble with this is it produces a single hydrogen atom at the end, and that's just not how hydrogen works. Hydrogen forms diatomic molecules like so, and that only makes sense if we have 2 hydrogens on the left, and now that we have +2 charge, that only makes sense if we have 2 electrons. So if you have the reduction of something like sulfur, hydrogen, oxygen, nitrogen, whatever, that forms polyatomic molecules, that's got to be reflected in the reaction you write. For metals, no problem, they always form monatomics. Cadmium 2. Beryllium 2. And calcium 2. All right, so there's our finished, nice redox table for those metals. Now for these, remember we're going from in all of these reactions, from our higher form to a lower charged form. So for W, the higher form would actually be 0, and the lower form would be the ion. So W would have to look something like W plus an electron turns into W minus. Is this diatomic? I have no idea. Examples of things like this would be fluorine and chlorine and bromine on the redox table. And some of those are diatomic and they pick up 2 electrons and turn into 2 of these, but I have no idea what well, this can't be the real W because the real W is the element tungsten, and here I think they're using it to stand in for something else. So I don't know if I should be putting 2's on this or not, since it seems to be made up. For Y, well, that one is diatomic. That one is Y2. And it turns into 2 Y minuses. You can see that here. So that one's got to be 2 electrons. For X, again, we see there's an X2 form. So that's a diatomic. And for Z, yeah, Z's another diatomic. Plus 2 electrons turning into 2 Z's, minuses. So is W diatomic? I don't know. They never do show what its finished form is, and it seems to be a fictitious element. So don't know what to tell you on this. If you ever see a key where this has twos in it, then they should have given us more information. But the key fact is you can do a ranking where each of these is based on, is it like W where it's really good at winning fights over electrons, or is it like Z where it loses all the time? Here we have Y tried to take electrons from W and couldn't. That makes W the champion. And Z, we see losing electrons to X. X loses electrons to Y, and Y loses electrons to W. So that's how we built up this order.